My name is Santiago. As I was introduced, I'm from Argentina. We have a small training company. We focus on data science for like high value. We do like a 3-month course to ramp up people that's been working with Excel or Tableau for years. So we introduce them into the data science world with Python. And lately, we are releasing a product that I'm going to show you. It's like a managed notebook, Jupyter Lab environment with a few more additions. Is specially tailored for education. We actually needed it, and nothing suited our needs, like Google Colab or Azure Notebooks. They're really good, but we needed something better. About this talk, I usually think, so this is what happens. We have a high profile company that says we want to ramp up someone into the data science world, and I bring my curriculum, and there is an entire class that is about data functional programming, and they're like, "No, dude, I want something practical. I want something that's useless, right? It's nobody. It's gonna. I can't feed my family with functional programming. Sorry." And the truth is that we are fairly nerds in this regard. We think that it's extremely important for every data science to have a good understanding of functional programming. And the cost benefit of it, it's impressive because it just takes a couple of hours. Today it's going to take 30 minutes. And usually people get a good sense of what it takes and what are the advantages of understanding how to work with functional programming because of the reasons you're going to see in a couple of minutes. This talk is going to, so we have 30 minutes, right? At the end, we have a couple of minutes for questions. I will actually try to take questions during the talk, so you guys are welcome to interrupt me. Please do it, all right? So if there is something that is not clear or something you want to comment, again, we do teaching for our lives, so it's fairly good to have you interrupting us. And what we're going to do in the end is a quick quiz with a couple of prizes. I brought alfajores from Argentina. I don't know if you know what it is. So I have 6 of them. They're fairly good alfajores from Argentina. So we will be doing a quick raffle based on the quizzes and your answers. So that's how it's supposed to work. So interrupt me during the talk if you have questions. So why is data science important for data science? Functional programming for data science, because what I've found during all these years working with it is that functional programming applies to something so small as, counting words in a text file to an entire data pipeline in a massive company. The process of managing data, of mapping it, reducing it, filtering is present everywhere, okay? So you're going to apply the same concepts, the same primitives to, again, your tiny code for a script that will, you're trying something in your home and it's going to open a door. The same code that's going to be applied in your machine learning pipeline, for example. So everything is going to work under the same foundation. So we think that functional programming is, for us, in our discipline, as developers, it's the theory of everything. I don't know if you guys are familiar with it. I'm not a physicist, but it's usually understood that there's this mismatch between the tiny world and the large world in physics. Well, that doesn't happen in programming. We have functional programming that applies in the same way to something extremely large, thousands of computers working at the same time, and something as small as your 200-line script to do something tiny. So we will try to define what is functional programming. Actually, we need a little bit of history first. It was inspired by lambda calculus. It started a long time ago, a long time ago. And the idea was to apply this calculus, lambda calculus, into the computing world without, with the same knowledge or the same concepts that we had in the most declarative and expressive mathematics world of lambda calculus. The first programming language was created by this guy. It was designed by John McCarthy. The first programming language, the first functional programming language was Lisp. There are a few others, but usually understood the first one was Lisp. And the truth is that this person designed the programming language. He didn't actually coded it. Pretty much the same thing that happens with Python. Python is actually a specification. It's the docs. It's a PDF. Then you have something like CPython that brings these ideas to life. Of course, that Guido is both developer at CPython and also the designer. But for example, right now, Guido I think, has stepped aside in the development of CPython, and he's just overseeing the PEP process. So the same thing happened here. There was someone that was designing the functional programming language, and then it was implemented by other people with different implementations, and their primary usage was in the 60s in artificial intelligence. Right? That's their idea. They wanted to bring artificial intelligence to life in the 60s, and they thought about this programming language. This person, people that had some training in computer science might know who he is, John Backus. We have the grammar and all that. He also had a functional programming language. It was called FP, and had this phrase in his presentation or dissertation. I don't know if it was a dissertation or the presentation of the language. And as you might see, is this idea of combining different functions, right? And it has a really mathematical root with it. Again, it's creating an algebra of programs. And I don't want it to be extremely mathy. It isn't. But it will bring home these ideas for those of you familiar with these concepts. There was actually, this is completely useless for this talk, but it's pretty fun. There was a machine built exclusively with Lisp, right? It was just a functional programming machine with all the primitives built with Lisp, and it was there were many innovative things like garbage collection or local area networks, and I think the first computer mouse was built in one of these. So it was pretty interesting. So about the definition, it's fairly difficult to define functional programming. If you guys get 10 different books about functional programming, you will get 10 different definitions based on what they think, what everybody thinks. So it's really hard to come to a really specific and strict definition. So we were gonna just give it a try, really high level. We're gonna say that functional programming is a style of programming, right, that will favor declarative programming over imperative programming. And of course, we're going to talk about that in a second. And it's going to make usage of immutability, right? No side effects, different things, but related. And also function composition. I want to talk about high-order functions in a second. So if we break down this definition, we're going to start saying that functional programming for us, at least, or for me, right, is a programming style. It's not that you're I don't know, you're a functional programmer, or this code is perfectly functional or purely functional, as might happen, for example, if you use something like Haskell, but that's not our scope. We are allowed to break the rules sometimes. That's fine. Sometimes you need pragmatism, and we're gonna make use of it. So it's a style of programming. It's kind of a mindset. It's a way to review code, right? When you're reviewing code, trying to find side effects that might be breaking your code, mutability that might be breaking this functional style. One of the most important concepts we have is both immutability and no side effects, as we saw before. The first one, immutability, and again, they're related but kind of different. Immutability means, or is especially related to the usage or in data. When you have data and you're mutating it, or when you're changing it. Our objective in functional programming is not to change data. And you've seen this a lot, hopefully. And usually it is actually presented as a kind of a two-path way to solve a problem. It's like sometimes you have to make the decision if you want to make something mutable or immutable. The solution is going to work in the same way. So here, for example, I have something really simple. There's just, I need to add a new element to a list. I can provide a mutable solution or an immutable solution. In the one on the left, the mutable one, I am changing the list L. It has one new element now. In the other one, I have created a new one. So the first list, L, is just clean, has never been changed. A few benefits from this is that you kind of always know how your code is performing and what the data behind your code is representing. And this is extremely important. If you stop the code at this given point, you can just understand and replicate what's going on with your data. If there are things changing it in between, you're not so sure. And so, of course, testable It's really important for concurrency and also the robustness that we're going to gain, right, whenever we apply these concepts for the purposes of a large system especially. Python has a lot of immutable concepts. You might know a few more. I have here a string. A string, for example, in Python is immutable. I can try changing it. Sometimes I have the illusion of changing it, but internally that string that was created, right, is never changed and actually has many benefits. I don't know if you guys have ever heard about the strings internals or internalizations or stuff like that, where there's actually one copy throughout the entire system of the string hello, and it's reused everywhere because it can never be changed. So that's a significant gain in speed and performance because of this simple decision. It was a decision when Guido, the creator of Python, started with it, said like, should we do strings mutable or immutable? And they say mutable, we gain all these benefits. So there are plenty. I don't know. Another example, immutable things in Python. Tuples? No? There are many. One of them, of course, the most important one is a tuple, frozen Z. We have different examples, and it's going to resound now in a couple of seconds. Pandas, NumPy, all these libraries favor immutability as much as possible. You've seen this inplace, right, parameter everywhere. If you try to do any operations in Pandas, it's going to return a new thing. It will not mutate it. It will not change it by default. And actually, they can employ very advanced ways of sharing data between copies to minimize the performance hit and still give you this sense of security by not changing the data. The same thing with NumPy. Actually, in our class, when we start the data science part, we have like an entire class about NumPy, the benefits of memory and performance with NumPy and all that. And we have like a 2-hour class, and when we finish, we say, well, a NumPy array is pretty much the same thing as a list. Can you guys tell me how to append an element to an array? It's like they say, you're cheating on us. We never saw it. How can you do it? And it's actually really hard. If you guys try appending a new element to an array, okay, modifying the original array, it's extremely difficult, right? There is no simple way of doing it with NumPy because it has big performance implications. NumPy tries to allocate a continuous, I don't know how to say continuous, right?
Yeah.
Yeah, thank you. Continuous place in memory where it should put all the numbers in it, right? So when it performs operations, all the memory is moved in the same kind of chunk, right? It's allocated and moved back and forth registers, CPU registers in memory, and everything is more faster, sorry. If you divide your array in multiple pieces, things are not so fast. So whenever you create an array in NumPy, it's sealed. There's actually a way to literally seal, and it cannot be changed in any way. Set flags equals right equals false. It would be really good if this thing was actually a way of like a global default. You could say I don't want anything mutable. There isn't, but that's what we have. Another similar concept is side effects. Side effects is pretty much the concept of mutability, but not related to data. Programming, managing systems, I've been coding for a long time, is just about computing and data. That's it. Data is for immutability. For computing, for algorithms, we have the concept of side effects, and it's what we should try to avoid. A side effect is any type you're accessing an I/O resource, for example. You're trying to read or write to a file, to the network, to any input or output device that it's out of your memory scope. The same thing as, for example, raising exceptions or changing object states. Sometimes you're not aware you're changing the object, the state of an object, or accessing global state, which is, of course, fairly bad. This is an example. I don't know if you guys can see it clearly, because there's a lot of light on the side, but the usage of side effects is also kind of a decision, and not so much as this decision like, at this point I'm going to decide to introduce a side effect. It's more about someone that is not so familiar with programming, and they find the quickest solution possible, and then they realize that there was a no side effect solution or a not mutable solution. In this case, we have a function that it's doing something. I put computer earnings, anything can be placed in there. But you're basically doing something, some operation, and you're adding a bunch of side effect things with it, right? So for example, you're accessing a global variable that it's the connection to the database. You're asking for an input inside a function, or you're printing in the function, you're writing the results, or you're reading the results inside that function that it's supposed to only do that thing for what it was created, right? So this is a clear, really clear, obvious example of side effects, and those are the things you guys should be looking for, right? These things about, this is not the scope of my function. I am doing something else that it's not of the scope of this function. A solution, right, is simple. It's usually trying to keep all the I/O, all the things that are related to side effect to some other different place. Like usually we say that a system is like an onion, right? With the outer layer being the one interacting with the file system, with the network, doing I/O, and everything internal should never be aware of that. So we usually say that if you can use the same code in your laptop, in your phone, in a Raspberry Pi, it should work in the same way. You shouldn't be changing the interfaces that it's accessing. The advantages of these ones is, of course, are obvious. Usually, right here, if this function fails in production, what's the problem? What failed? Did it fail that maybe the user input the wrong year, or the database broke, the database connection broke, or it was inconsistent? What was the problem, right? If you have something that it's like this, you can always test it differently, like separately. You can have absolute logging for that. It's like you can have a more design-oriented, contract design-oriented software where you say, this is the input from what I'm receiving, you can log it. This is what happened, this is the output. Is everything fine? If the input was what you knew it was and the output wasn't, your function is the one with the problem. Maybe when you read the logs, you see that the input was different and maybe the problem is in the database, but your function is not responsible. You can go look to some other place. And again, you can reuse it in every other situation. A really important concept of side effects is that it introduces complexity, which is, those of you a little bit more familiar with the software development process and engineering, you will know that complexity is this word we all fear, right? Complexity is the worst thing can happen to a system. And picture, this is a pretty simple, this can be either a big ETL process, a big data pipeline process, or it can be just my code, right? It can be functions calling themselves, or complete like jobs being invoked by different ETL processes. Doesn't matter. But what happens if each one of these could have a side effect? Like these, I don't know, green bubble could modify a variable in the red bubble. It's complexity. We don't know what's going on. If we stop the system right here, anything can happen. We don't know when something is being changed. That's why, again, usually we try to keep like side effects to the ends, and everything in between should be a little bit more pure, which is what we're going to talk in a second. There's actually a list of really bad software bugs, and one of them was the Thirac25, a machine that killed people with a side effect. That was the issue. All right, there was a variable that was modifying state and was creating a race condition without people knowing about it. It was impossible to test because it depended on the user input, and it was, of course, a really bad execution. I hope nobody ever gets to this. But again, it's proved. There's actually a paper linked right here. There's a paper, a really good explanation of why side effects might contribute to complexity. So how can we get rid of these side effects? By the usage of pure functions. This is also a highly functional programming concept, pure functions. And they're basically functions that they don't have side effects, period. And that by any input, by the same input, it's always going to produce the same output. Doesn't depend on the day, doesn't depend on the platform. It's just a pure function, like a mathematical function. 2 + 2 is equals to 4 everywhere, all the time, right? And that's not a function, but the addition of 2 + 2, the same input, is going to always give you the same result. The good thing about have pure functions, as simple as they are, right? Again, sorry to introduce them, to even waste a minute introducing them, is that they're going to have a ton of benefits, right? Benefits as simple as being testable again, or more advanced, like being able, we can cache them, or we can build parallel versions of these functions. Testing them, we know it. We can compose them, right? So in this case, we could even, if we have specific tests for add, we know it works, we can derive other functions out of it, and they will work, right? Yeah.
10 minutes.
10 minutes? Seriously?
Yeah.
Oh, man. Okay. I had a ton of important things. Seriously, 10 minutes?
Well, 10 minutes until questions.
Oh, until questions?
Yeah.
Oh, so we have 20 minutes elapsed?
Yeah.
Okay, good. Okay. So really quickly, referential transparency, you can look that up later. It's not that important. It's basically replacing the execution of a function with its value. It should be the same thing. It's related to pure functions. And back to the definition, I had something really important that was function composition. I will leave it up for later. The slides are posted. You guys can see them. Basically, a high-order function is a function that is when you're passing a function as a parameter, or you are, for example, returning a function from another function. So that's something that it's possible because Python treats functions as first-class objects. This is a really important concept. In Python, for Python, a function is just another object, like an integer. Can you assign an integer to a variable? Yes, you can do the same thing with a function. Can you store an integer in a list? The same thing can happen with the function. Just a plain old object. Python doesn't differentiate it in any way. So yeah, we have a couple of examples there of that. So going back again to the definition, we have pretty much the most important concept, that is declarative programming. Favoring declarative programming, the best way to understand declarative programming is by understanding imperative programming, that it's pretty much the other end. And it's when you're giving the computer the precise instructions of what it should do, okay? So for example, we have two robots that are gonna cook for us. One of them is the imperative robot, and the other one is the declarative one. The imperative one, we should give to it each one of the instructions step by step. Imperative programming was thought to code machines. It was a practical solution that we had back in the 50s and 60s when we had to say, take this piece of data, move it to this register, add it to this other one. We had to manipulate all the instructions one by one. This has many problems. You, of course, know about it. We're going to go again to it. What happens if, for example, I interrupt the code? You don't see what's crossed, right? And I ask you, do you know what I'm doing right here? If you're reading an algorithm that it's not 4 lines of a robot cooking, it's a real function in your company that has 200 lines, and you are reading it, and someone interrupts you and say, hey, we don't have more coffee. You say, I was in the middle of reading it, now I have to go back and understand everything again. It's because you're following the steps one by one in your mind. The imperative feels like micromanagement. It's like you're telling the computer what to do, or how to do it actually, how to follow the process you want to achieve. Declarative is the other end. It's usually you tell the computer what you want to achieve, right? It's like, I want you to build this thing for me. And in this case, it's going to look something like that. For example, computing the matrix with a vector product, matrix vector product. This is the code with, this is an imperative solution, just giving the steps, right, one by one, explaining the function, how it should execute each one of the steps to achieve the result. And this is going to be, of course, the declarative solution. I want the product between this matrix and this vector, right? It feels like cheating, of course. It's like with the declarative ones, like there is no magic function for everything. It should be amazing to have them. And actually, this is kind of the key as programmers, understanding the level of abstraction we have. It's like, can I ask my computer? I can ask my computer to do a simple matrix vector product. Can I ask my computer, I want a clone of Amazon built with Django? It's going to do it? No, of course not. That's too high of an abstraction. So the key here is, again, balancing the level between something that is too high level and something that is too low level. As usual, you try to stay as high as possible with your levels of abstraction. The three most important abstractions in functional programming you're going to see everywhere are map, filter, and reduce. These are pretty known. Map is a function that's going to take both a collection and a transformation function that's going to apply this transformation to each one of the elements, producing a new one. It's transforming each one of the elements one by one, right? It's transforming each one of them. If this looks familiar, by the way, this is the regular map function, the standard library in Python. This is how you call it, function plus collection. If this looks familiar, it's because it's just a regular list comprehension in Python, right? So list comprehension in Python is just the application of map. And it's also built into NumPy and pandas. It's a regular vectorized operation. You have a collection, you just express what you're going to do. I don't know, multiply these number with these thing and I don't know, subtract that. You're just passing, right? You're declaring what you want to achieve. You don't care how it's going to be done behind the scenes. Filtered, it's other important, like low-level core function in functional programming. It's the standard library version is that. It receives, as usual, a function in the collection. The well-known version of it is also a list comprehension with the predicate part or the if part at the end. And also, you folks have probably seen it too with NumPy or pandas when you are doing a Boolean array or a mask. You're saying, you're expressing what you want to get. I want to get from this array everything that is greater than 2, period. I don't care how you do it. Maybe behind the scenes, NumPy is parallelizing it. Or it's, I don't know, doing some crazy matrix mask in it. I don't care how it's doing it. I'm expressing what I want to achieve. And finally, reduce, that it's just also called fold. It's combining things. Final comment here is that it's no longer part of the standard library. There is in the slides, there are notes with some quotes. There is actually a post of Guido saying that it was too complicated, so they removed it, and now it's part of the functional module. And if mapping, reduce, and all these core languages, components of functional programming sound familiar, it's because, again, we use them for tiny, tiny, tiny code, doing something really tiny for our own script, or for large systems. It's the same thing. Map, reduce, filter, it's always pretty much the same thing. This is, for example, a good illustration of a map, reduce, a Hadoop job to count words. The hello world of Hadoop is counting words. So this concept applies for, again, multiple machines, or it also applies for just one machine working, again, in the same way. How much time do we have?
Let's go ahead. 12 minutes.
Okay, good. You made me scared before. So, what are the differences between map, filter, and list comprehensions? We will not have a lot of time to talk about this. Is that right now in Python 3, map, for example, is going to return an iterator. It doesn't actually return the objects as soon as you get them. So I have right here an example. Where is it? Let me see if I can. So this is, I don't know if you can see it in the back. This is what a map is going to return. And what it actually returns is this iterator object that you are the one supposed to pull the objects from, or the results from it. It's not just going to compute them at the moment you ask for it. That's because it's a lazy evaluation, right? It's trying to evaluate it whenever it's necessary, not as soon as you invoke it, because again, maybe you don't need to use them right now. Maybe you just need the first 2 elements, not all of them. So this concept of laziness is extremely important in functional programming, and it's also related to the concept of referential transparency. Okay, any questions? Good? Too boring? No? You guys are good? All right, pull your phones. We're going to do a quick challenge with, I hope you guys paid attention. So you have to go to this site that is kahoot.it, no affiliation here, just so you can see it. How can we kill music? And once you're in the site, you should there you go. You have to enter this pin. Right here. So I didn't lie. 45. Ready? Ready? Really hard questions here. There's lots of code, imperative code. You guys have to read through them. All right, 66. Should I start? There you go. All right, so the questions, I think they're gonna appear right here. And I think we can get started. There is one question at the beginning for you guys to familiarize with this site that it's not really intuitive. So what's the result of 2 plus 2? Of course 4. You guys will have to hit the triangle, the pyramid in your phones, right? It's going to give you 10 seconds per question. There you go. Good, nobody, no. Somebody doesn't, you guys don't like Forest? Okay, next question. Who was the creator of Lisp? Oh, some people weren't really looking at the slides. All right, FP, functional programming, was inspired by? Who hit the green button? I completely made that one up. What are the advantages of immutable code? Definitely blue. Definitely blue. All right. Actually, some of these questions are going to have 2 possible answers, so both these are good. It's whatever resembles first. So Dan is running. Who's Dan? Good, Dan. You were followed closely by someone, I didn't see who. Which of the following Python types are immutable? Again, 2 possible answers. All right. Lists? Who's mutating lists? Who thinks lists are immutable? You're going to have a bad time. All right, John. Oh, Dan. Sorry. We have 6, Dan, so it's going to work. John, Alan, Dan, Sonny. Alan? Alan, where's Alan? You're the guy from the book. I have your books. Yeah. You have AlphaHorse for free, you don't have to play this thing. Okay, which one of the following are considered side effects? Ooh, 40 modules. We're pretty much done. Which of these are the characteristics of pure functions? Pure functions. Whoa. Blue, Oh, you stop playing, right? Okay, we're gonna give 5 alpha for the first 5, and he's gonna get 1. The characteristic of functions first-class objects. This is the final one. Almost done. Good. Someone was trying to test them with PyTest. Are we done, John? No. Oh, 2 more. Which are the following core functional programming functions can be replicated with less comprehensions? Fall and reduce can't, sadly. There's a tiny difference between fall and reduce. It's actually in the slides, but I was in a hurry, so I didn't cover it. And finally, what's the difference between a less comprehension and a generating comprehension? We didn't cover this, so sorry about that. It's also in the slides. We should not count this one. Generated comprehensions are lazy. That's the idea. Actually, we can see an example later. All right, so Henry, who's Henry? Yeah. We have 1, 2, 3. Let me get the first 6 people. Ste, Ken, MH, and Boo. Who's Boo? Boo. All right. A big applause for everyone.